this and say, welcome, we're going to do circular motion notes. So a few things to be mindful of with circular motion, what the big idea is. So uniform circular motion, UCM, occurs when an object moves around a circle at constant speed. Non-uniform circular motion occurs when you go around a circle and you're speeding up or slowing down, you know. But if you're just coasting around a circle, you have UCM, uniform circular motion. Newton's laws apply to, you know, everything, so they certainly apply to uniform circular motion. We're going to think about what happens when we end uniform circular motion. Let's say that I'm swinging, say, a bag on the end of a string, and somehow I manage to cut the string. What kind of motion does the bag follow? We'll talk about that. And then we're going to do 4 classic cases where we're going to do soap on a rope, conical pendulum, flat auto track, or a banked auto track. And you'll get one of those 4 on your test, I can tell you that. There's going to be some kind of problem. Now, in each problem can ask you like 3 different things. So there's like 10, 12 or 20 permutations. I could probably ask you 4 or 5 things if I pushed it. So there's not just going to be the problem that I ask you. There's going to be differences, permutations on the same theme, but there's 4 different setups. And then once we've done that, we'll talk about non-uniform circular motion. And then we might get to motion accelerating frames. Sometimes I teach it, sometimes I don't. Of all the stuff we do, it's a little bit esoteric. It's kind of like it's the kind of like a bit of the gee whiz type physics. It's interesting, but. And again, it's Newton's laws. It's all Newton's laws. So uniform circular motion. So, okay, here's a vector diagram. Well, a setup with vectors on it. So here's the circular motion. I'm going at constant speed. So that means the vectors for my motion, my velocity vectors, must have the same length. But because I'm going around a circle, they're not in the same direction. They're tangential, of course, to the circular motion. If I'm going around a circle, my velocity is in front of me. It keeps on changing direction as I go around the circle, but at each instant my velocity is in front of me. So the directions are not the same, but the size of the vectors are the same. And if I remember, v acceleration equals vf minus vi, and acceleration is a vector, and vf is a vector, and vi is a vector. I'm sorry, over delta t, just ignoring the delta t. So, okay, so vectorially I need to find my vf. Well, there's my vf. And vectorially I need to find my vi. Well, there's my vi. And then I just add, let's have a look. I put down vf, and I add the negative of vi. This equals vf added to minus vi. Remember that? We don't know how to subtract vectors, but we do know how to add them. So I add the negative. So then I come down here and say, well, there's my vf. And if vi is pointing up and to the right, then minus vi is pointing down and to the left. And the sum of those is this purple little arrow, which points from the beginning of the beginning to the end of the end, just like we've been doing in vector diagrams. And that's my change in velocity. So take that change in velocity and divide it by the time, and there's your acceleration. So my acceleration will be this vector divided by the change in time. It'll be bigger, or well, it's going to be smaller because I'm dividing by a change in time, which is, say, more than 1 second. But it's going to be in the same direction. So if I look at this direction, I see that, well, actually it's pointing down to the middle. There's my acceleration. And it points towards the middle of the circle. So the first issue that people walk in with is they've probably heard of centrifugal acceleration or centrifugal forces, and I kind of wish you hadn't. It's like it's a fictitious force. It's not really there. It feels like a force, but you know, there's lots of things feel like a force. Well, not a lot of things, but there's some things that feel like a force. And I think it's kind of like confusing. So I'd like you to kind of like dispel that from your vocabulary. And I'm going to talk about centripetal stuff. Centripetal, P-E-T-A-L. It's like the petals of a flower all point towards the middle. So centripetal acceleration points towards the middle. So, and I try not to talk about centripetal force. I'll get to that why. I like to talk about centripetal acceleration. So a body that moves in a circle has centripetal acceleration, must have, not may have, not perhaps it has, must have. If you're going in a circle, you are experiencing a centripetal acceleration. Whether you're speeding up or slowing down, by the way, if you're going in a circle, there must be an acceleration at 90 degrees to your motion. And if you're experiencing an acceleration at 90 degrees to your motion, you must be going in a circle. So one, you know, if you're going in a circle, you must be experiencing the acceleration. If you're experiencing the acceleration, you must be going in a circle. Okay, so centripetal acceleration is directed towards the center of the circle. If you are speeding up, then you could have an AC, and because you're speeding up, you can also have an AT for atangential. If you're constant speed, you only have an AC. AC has no component along the direction of motion at any instant, so it doesn't tend to speed you up and it doesn't tend to slow you down. So if you're going in a circle, whether you're speeding up or slowing down or whether you're coasting, you have a centripetal acceleration. And the magnitude of the centripetal acceleration is v squared over r. And where does that come from? It comes out of a hat. I frankly have no idea where it comes from. I've never looked it up, but that's where it comes from. The speed squared, v in this case means speed squared over r. Of course, the velocity is changing for every instant, but the speed is not in this case because we're doing uniform circular motion. So let's do something with it. What is a centripetal acceleration experienced by a 5 kilogram mass that moves at 12 meters per second around a circle? So the radius is 4 meters. And if you like, here's my mass. And the mass is 5 kilograms. And it's traveling at 12 meters per second. And I want to know what is the centripetal acceleration. AC equals question mark. Tip. Whenever possible, put your mass at the right-hand side of your diagram because it makes the signs a bit easier to work with later on. For this thing, it doesn't matter much. We say, well, AC is equal to v squared over r, which equals, now, I'm going to look at my diagram. I'm going to go 12 squared over 4, which equals 144 over 4. AC is equal to 144 over 4 is 36, I think, yeah? 36 meters per second squared. And again, that's the magnitude of it. When I'm down here, it's going to be a different direction, a different direction, different direction, different direction, but it'll always be the same size. So it's not your vector. I've not got a positive vector acceleration. I've got a magnitude of 36 meters per second squared. If I chose to visualize it here, that would be a positive 36 meters per second squared. But if I put the mass over here, it'd be a negative 36 meters per second squared because I've got a different position for my mass. Now, if you get to this stage and you know the equation, but you can't think of the equation, a tip, I'll just keep going back to it, is a tip is put down what you know. I know my mass equals 5 kilograms. I know my speed is equal to 12 meters per second. Let's have a look. I know my radius equals 4 meters. And I want to know what my AC is. And you'd be surprised at how often that will just jog your memory. And you go, oh yeah, of course I know what it is. But without the list, then it's not so clear. It's all kind of in your head. And if you're not doing a diagram and not doing a list, then you basically, sorry. And you basically, I have allergy injections, and they always phone me at this time every week. So you guys get stuck with it every time, and it's like, I've got to remember to turn my phone off. They want to confirm the appointment. So if you're not doing a diagram and not doing a list, then it's all in your head. And I don't know what do you write down an equation sometime? You're doing all that stuff in your head. I don't do that. I draw myself a diagram. I make myself a list. In truth, as time passes, I don't need the list so much because my diagrams are pretty clear. Here's an interesting point. I did not use the mass. Yeah, that's the way it is. You didn't use it. It's like you don't need it. AC equals V squared over R. No mass involved. Don't worry about it. So watch out for that. I'm not above. My questions are linguistically simple. I try not to put extraneous stuff in. If you look at the back of the textbook, they have, Johnny the dentist does this, and then at the end they get to the bit you need for the question. And I find that frustrating. The idea behind those back of the chapter problems is they're designed to appeal to you as an engineer or, on the other side, as a life science person. So they write the questions with that in mind. And then there's a tradition of throwing people some mathematical curves so that unless you remember this trig function or unless you remember this thing, then you don't spot it. So they tend to take a long time. And at some point I just decided I want to test people's physics as efficiently as possible. So I made all that preamble stuff just go away. And frankly, the thing about the mathematical little tricks is once you've seen them, you remember them. So the first time it's an intelligence test, and the second time is did you remember it? I don't care much for that. And so my questions become quite short and to the point. And then what I learned the hard way, because some students pointed out to me, was unless I put red herrings in, unless I put extraneous information in, then frankly you can just say, what did he give me? And then, Whereas if I put this extra information in, you've got to think a bit more about it. You've got to visualize it. You've got to be an engineer about it. You've got to say what's important, what's not important. So watch out for that. I like to do that. And then there's another skill here that engineers have, and that is they go seamlessly between, or the good ones anyway, go seamlessly between equations and graphs. And I think our tradition is we tend to do graphs somewhat, and we focus on equations. And I think it's a bit of a shame, especially because, I know from my days in industry, graphs were really quite useful. And my wife to this day will say that she gets students and she just wishes they knew more to do with graphs. Maybe they didn't need such advanced math in other areas, but she wishes they could read graphs better. So it's a useful skill. So I want you to get used to going backwards and forwards between the two. So here's a typical example. A block of mass M moves in a circle. So here's my block of mass M, and it's moving in a circle of radius R. So here's my radius R. With a tangential speed, so here's my tangential speed V. What trace best represents the relationship between the block's centripetal acceleration? So look at your axes and tangential speed. Oh, okay. So we're looking at my AC and we're looking at our V. Okay, so those two. What relationship links those? And I know that AC equals V squared over R. And some people can look at that and they can look at those choices and they can say, oh, yeah, it's A or it's B or whatever. So what do you think? Anybody want to be brave and give me a suggestion of what you think it is? Which one of those is best? It's going to be E, it turns out. It's a squared relationship. But let's say you didn't spot that. Then what would you do? So first of all, it really helps to rewrite your expression. So I'm going to have AC, and then I'm going to go against V. So do it like that. Do AC equals something to do with V, and then I've got this 1 over R. Well, 1 over R is going to be a constant, so just, put that in a little parentheses, and it's just 1. And then, oh yeah, I got to square this. If I didn't have to square this, it would be linear. It would be y is equal to mx plus b. It would be linear. I got to square it, so it's going to be a squared relationship. Yeah? If I square rooted it, it would be c. If it was linear, it would be d. If it's squared, it's e. If it was inverse, if the v was on the bottom rather than being on the top and it was just a v, it would be a. If v was on the bottom and it was a v squared, it would be a, because I can't tell the difference between them. It's not b. I don't think it's ever b, but, but let's say that didn't help you with it. What would you do? And this is a skill I'd like you to develop over time. What you do is you'd say the answer is AC, and I'm starting off with V, and I'm getting there by having V squared. And you look here and you go, well, let's let there be 0, 1, 2, 3, 4, 5. And then you say, well, hold on. If V is 0, V squared is 0, and 0 times a constant. Call the constant 1. Just why not call it 1? It's a constant. Who cares? So 0 times 1 is, so V squared is 0, and AC is V squared times 1, which is 0. If V is 1, then V squared is 1. So then AC is 1 times 1, which is 1. If V squared is 2, then if V is 2, then V squared is 4. AC is 1 times 4, which is 4. If V is 3, V squared is 9. AC is 1 times 9. If V is 4, V squared is 16. AC is 1 times 16. If V squared is 5, if V is 5, V squared is 25. So that's 25. So now is the thing. This is where people make a mistake sometimes. AC, and I'm plotting it against V. So my V column goes 0, 1, 2, 3, 4, 5. And then my AC column is 0 to 25. 5, 10, 15, 20. And so now I start to plot and I go, well, 0 gives me 0, and 1 gives me 1, and 2 gives me 4, and 3 gives me 9, and 4 gives me 16, and 5 gives me 25. And you can see there's a nice curve to that. And so you can see what it is. Most common mistake, people will do this and they'll go, well, oh yeah, AC and V squared, because they'll go AC and V squared. They're looking at the expression, they're not looking at the graph. And so they'll go 0 plays 0, and 1 plays 1, and 4 plays 4, and 9 plays 9, and 16 plays 16, and 25 plays 25. And get me a linear line, because they're plotting the wrong thing. So you've got to have a little bit of discipline here, and sometimes I find it's helpful to actually get yourself a highlighter and highlight that, and then here highlight that and highlight that, so you don't mess up. Highlight that and highlight that, but not the squared. The squared is something that's done to the V. I could ask you to plot AC versus V squared, and it's a straight line. So you can't remember the equation gives me this shape. It depends what I ask you to plot. So there's the skill. I want you now to be able to pick the trace. Later on, I'm going to basically give you, I'll give you a grid. And it will just have AC, and it will have V, and it will have a series of grid lines. They'll be straight. And then I'll say, plot me a graph. And people will freak because they'll go, well, what numbers do you want me to choose? And I'll go, I don't care. Choose numbers. Well, how do you know if the answer's right? Oh, I can tell if the answer's right because it has a certain ratio to it. There's a certain swoop to it. So whether you say 0, 1, 2, 3, 4, 5, or 0, 5, 10, 15, 20, 25, I can figure it out. I can look at your graph and tell if it's right. So for me, it makes no difference. But for you, you got to decide what numbers to use. And that's a different skill set. And when people first start doing that, they just feel incredibly uncomfortable. Because all your careers, you've been trained to, here's the number, work out the answer. And now I'm just giving you a grid and saying, you figure it out. And just make sure what you do is consistent. You can call 1 over r whatever you like. You could call 1 over r 0.027. As long as you do it for every one of them, it will be right. So, but it's easier if you call 1 over r1 because it's not changing. So some different skills. We'll head there. We're not going to get there like this time, but you know, you might want to start prepping yourself for that, because especially in physics too, I like to see that. Cool. Another skill. Let's add another skill, and we're doing for time. Yeah, another skill. Engineers don't always know what the absolute values is, but they know they doubled it and they tripled it and they quartered it. So let's do a situation like that. So we say a block in a circle. It has a centripetal acceleration of 9 meters per second squared. What is the centripetal acceleration if a new block, if it has triple the mass? So we'll have more mass, and it has 4 times the velocity. Well, there's the old velocity, and we have 4 times the velocity. There's the v old, and there's the v new, if you like. And it follows a path that's twice the radius. I don't want to take up my, I'm going to cheat a bit. I'm going to say, it takes up twice the radius. So bigger radius. Here's my new radius, and here's my old radius. And here's my new mass, and here's my old mass. So what on earth do I do? First thing I do is write down the equation. So I know for this, acceleration, AC equals v squared over r. So then I say AC new over AC old equals, well, actually I have a number for that. AC new over, it's the only number I do have, over 9 is equal to, well, it's the ratio, the answers is equal to the ratios of the left-hand side must equal the ratio of the right-hand side. Oh, so this is V new squared over R new divided by V old squared over R old. Okay. So my V's, I don't have numbers for the V's, but I know that four times the velocity. The new one is 4 times the velocity. So that would be 4 and 1. I've got to square them because the equation says to square them, but it's 4 and 1. That's the simplest way. You could say 1 and a quarter. You could say 20 and 5. You could say 16 and 4. You can say whatever you like. You could say 4m and 4v and 1v if you want. But you might as well just pick the simplest ratio you can. And then for the radii says twice the radius. So that's going to be 2 and 1. And it's the ratio of those two. So that's going to be 16 over 2, which is 8. So then carrying this on a bit, so AC new over 9 is equal to 8. So AC new is equal to 9 times 8, which equals 9 8s is 72. What are the units going to be? Meters per second squared. And of those people who, well, let me just catch our breath for a minute. So of those people who know what they're doing, who know the equation, kind of like they've got the equation down, they've got the idea about using the ratios, the most common mistake is that they'll tell me that the answer is 8 meters per second squared. And what's going on there is, when you look at their work, they're not writing the full equation down. They're doing like phrases. I think of this as phrases. That's a phrase. It's a bit of work in. It's not an equation. It's a bit of work in, and it's mathematical jottings. And they get the answer 8, and then they go, oh, they got the answer, so they put down 8. And what they're forgetting is that that is the ratio of the new acceleration over the old acceleration. And if they thought in sentences, that's a sentence. That's, if you like, a complete thought. It's that, which equals that, which equals that, which equals that, which equals that. And there I say, oh, I'm also going to think in sentences. I want ACN equals. So I'm simplifying my sentence, but it's the same sentence. There are three versions of that same sentence. And so I don't lose track of that 9. And that's not genius. That's just practice. That's just being prepared to dot your I's and cross your T's and just get in the swing of things. And not being fearful that, man, that must have taken an age to write down. It takes no longer than, all right, maybe a little bit longer. But man, you make few mistakes. You know, I think the first person walked out after 30 minutes and the last person walked out after an hour or something like that. You got time for this. So just slow down a bit, write down all the steps. For one thing, if you make a slip, I can find it. If you just give me, a few little numbers and an answer, you're kind of on your own. I don't know what the equation you used. Sometimes I can figure it out, but sometimes I can't. So it's not like the more you write down, the more you will reveal in terms of mistakes. It's not a glass is half empty business. The more you write down, the more you will reveal in terms of what you've achieved. And if it's a small slip, if it's a transcription slip, in your thought 4 and then on the next line you put down 3, I can see it when it's on the page. When it's in your head, I have no idea that you were thinking 4 and then you just glanced up and you saw 3 and you put 3 down. So transcriptions, I can just say that's a transcription. That's okay. I can live with that. Very occasionally, somebody will make 2 mistakes that cancel. And I'll go, well, that's wrong and that's wrong. So, But that happens like once in a class in a semester where 2 mistakes cancel. It's like, one person, one time in one test in an entire class. That will happen. So write more down and you'll benefit from it. One of my childhood memories is been on a merry-go-round and been thrown off by my brother, 5 years older than me, and watching as I went away from the merry-go-round, him just smirk at me as I went flying through the air. He wonders why I still am a bit kind of like resentful, but and so if you'd asked me, what's your journey when you stopped going in circular motion, I would have said it was that I just went away from the merry-go-round. It was like, in reality, what happened was he pushed me off, and as I continued in a straight line at constant speed because of my inertia, as I moved, he swung round, and I just turned my head to keep looking at him. But the fact of the matter is if you break whatever is causing you to go in a circle, if you get rid of the friction force in my case, or if he was swinging me on a piece of string, the tension force in the spring, or if you could cut the gravity force between the Earth and the Moon, then the object that was going in a circle will no longer go in a circle because of there's no centripetal acceleration anymore. And so it will coast in a straight line for as long as, until it hits something, basically. And so you get a tangential journey if you end uniform circular motion. So in uniform circular motion, a centripetal acceleration must always point towards the center of the circle. In circular motion, I can actually say, centripetal acceleration must be provided by a force such as a tension force in a string, or my friction force as I stood on the merry-go-round. If the string is broken, the centripetal acceleration is lost, and the object no longer constrained to move in a circle. The object is in equilibrium, and thus will continue in straight line at constant speed. Given the situation's geometry, the straight line is tangential to the previous circular path. So, nice conceptual question. People will give me that, or sometimes they'll give me that, or sometimes they'll give me that, or sometimes they'll give me that. And I remember when I was a student kind of scratching my head and going, which one is it? I can kind of see all of them. But that's because I live in a friction-filled world, and so maybe I think that, well, I'm kind of going in a circle, so I don't go in the same circle, but I kind of do a bit of circular stuff. And this one I'm kind of saying, well, I've seen footballs curve that way or that way, so maybe I'm like a football, I'm curving that way and that way. Or this is where, no, I remember looking back and seeing my brother. And they've all got some logic behind them. But we don't live in a friction-filled world. As far as physics is concerned, on this anyway, we're going to go in a straight line with a tangential situation. Let's have a look. We've been doing almost an hour. I've got 30 odd minutes. I'm going to take a break now. So let's do this. 31.